Well, looks like we can start. Welcome back, everyone. So for today's class, we're working through section 7.4. I posted the section 7.5 notes just in case we can start a couple problems there, but I think we'll mostly be in 7.4 for today's class. Then other interesting thing to mention in the announcements. In 2 weeks' time, this will be week 5, we'll be having our first exam. So starting on about Friday of this week, probably going into Saturday, I'll start uploading the information here to say the exact coverage of exam 1. I'm thinking about ending it up to section 7.5. So 7.1 through 7.5 consists of a pretty good exam. I'll also post the sample exam problems and things along those lines, like we mentioned before. And one of the things I want to make sure that gets done right away, and first and foremost, first document I want to put here is the formula sheet that's going to be included as the last page of the real exam. That way, if you wanted to start early, you'll know what's included on the exam as a formula sheet and what elements that you have to be prepared for as you study. Well, that's a kind of a short announcement. Any questions so far, folks, before we get started? That's a great question. So for everyone that's here in class right now, primarily section 4, it'll be an in-person exam in this classroom. That's correct. This will be, I actually had some announcements related to that. I'm glad you mentioned it. It's officially a 67-minute exam, but I usually round that to 70 minutes. I ran this by the department chair because this is a fairness issue in a real sense. So it's officially 70 minutes, but I've gotten into this habit that's really hard to break where I just hate rushing people. I always give people 5 extra minutes. So it's really effectively a 75-minute exam. But for the people who are coming in through Zoom, the online section 44, it's an in-person exam as well. It has to be in a testing center. That's tricky if I'm effectively giving 75 minutes here. I have to make it 75 minutes in the testing center just out of fairness, because those testing centers do not give extra time. It's right down to the minute. They're kind of very specific on the times there. So what I'll be doing as we are getting course closer to the weekend is contacting everyone individually just to make sure the Pocatello Testing Center is the closest testing center next to you. Or if you prefer to take it in Idaho Falls, even if you're registered in 44, sometimes that could happen, and vice versa. So that's pretty much how the testing will be in for this class. It's kind of confusing because once again, it's really 2 classes we're doing all at once. Other questions about that so far? Okay, aside from the exam, another excellent question folks have about the exam is how long is it? Usually what I'm trying to do when I write the exam is I'm going for an exam, if it's a 75-minute time length, I'm really trying to write about a 55 to a 60-minute exam. So I'm always trying to build in extra time to double checking your work, that kind of stuff. So what would that look like? Probably about 6 to 8 questions. I solve those questions myself to make sure they make sense, the algebra doesn't blow up or anything weird happens, that the length of it is about right. And so these exams aren't meant to be you're writing as fast as possible to the minute. There is time to deeply think about what you're doing, the next steps, and that kind of stuff. But we'll get a good idea how it goes after the first exam. The following exams will be very similar in spirit to those ideas. For now, we're getting back to example 2 on these notes. So let's jump back in. Let's clear this out. And here's where we left off. Again, this is a rough spot in the notes because the partial fraction decomposition theorem is a really big statement. It has multiple cases. It goes from case 1 down through case 4. And so we have to know what's going on in each one of those cases. In this theorem, the only thing that is really critical that we watch out for is we are not in this situation where the numerator is of higher degree than the denominator. That's the case. Partial fraction decomposition doesn't even apply. We should long divide first and then just integrate what we have. So that's what's being stated right here. The numerator, r of x, has to be less in degree than the denominator, q of x. So think of the denominator as being the more important polynomial in your whole rational function. If that's the case, Well, there's three other cases to take a look at. You'll notice that what's highlighted in yellow, it's always referring to the denominator, assuming that the numerator is less in degree. What we're working on is trying to break this down to see what the factors are. Case one says all the factors are distinct, so I can't have x plus 5 and an x plus 5. It would be an x plus 5 and an x plus 4 to make it distinct. And they all have to be linear, so power 1 on every single factor. So if we were to try that out on this one, here's how it would go. Our objective on example 2, same as the first 4 homework problems in this section, is we're just writing down the form of the decomposition. We're not going to actually solve the numerical values for the coefficients. So this example is all just knowing how does it work before you solve, in other words. And this one's kind of annoying because what case 1 says is your denominator ought to look like that, factored into a product of linear factors. Those factors in the denominator get distributed through these terms that you see right here. So let's give it a try. We focus on that denominator. First, we have to factor. So this turns into x plus 5 to start. In factoring out that denominator, I would almost always say go for the greatest common factor first if you spot it. It would be just x in this problem. So x factors out, leaving behind 2x squared minus 5x minus 12. Next, we'd have to factor this right here. We're going to obtain an x plus 5 divided by x times two binomials. We can go 2x and x to start. Because of the opposite sign here, we have to have plus and minus. I think it should be minus plus, because 12 factors nicely as, say, how about, I'm not too sure what would work on this. Maybe a 3 here, maybe 4 here. That would give us, let's see, 2x by 4 gives us 8x. Negative 3 by x gives us negative 3x. I know it's not exactly correct, but I'm happy with what we had got. 3 and 4 does the job. My signs are just mixed. So just go plus here, change this one to minus. That has the effect of making that a negative 8x, a positive 3x for a negative 5x, which means we hit the middle term. We've got a factorization down. So each one of these positions right here are just parts of the denominator. Our end answer would look like this. It equals a1 divided by, first, just this linear factor here, x. Then we could say a2, or you can go a and b, really up to you. They have to use a1, a2 subscripting because there is no guarantee how many factors this could potentially be. So next one, it's going to be a2 divided by 2x plus 3 plus a3 divided by x minus 4. So that's the pattern of the decomposition theorem. If we were doing the full problem, that's going to be example 3. We would then have to solve for a1, a2, a3, plug in the results back, and then just integrate term by term by term. So that's pretty much the idea of the partial fraction decomposition theorem. This is a complicated antiderivative. But if you could separate this fraction, split it up like this, each of the antiderivatives here are very, very attainable. So case 1 comes up quite a bit, especially in exams, because these can be pretty long problems. Case 1 is usually the faster problem. And the thing that's most important about case 1 is that the factors were distinct. We lose distinct factors the moment we say that there's an x minus 4 squared or an x squared, for example. That takes us to repeated factors in case 2. Any last questions, folks, with our part A? Okay, watch out for these, by the way. This could be a real exam problem where I'm not asking you to do the full question, just indicate the form of the decomposition like this, but you have to be ready to go on factoring. So that can be sometimes a tricky element of the problem if you're a little bit rusty. We'll practice on factoring each time it comes up. So next most exciting case is case 2. And here in case 2, we're not looking at the entire denominator q of x. It says the denominator q of x is a product of linear factors, some of which are repeated. And we're supposing that's the repeat factor, ax1, x1. It's repeated r times, which means it would come up in your denominator as a1x1 plus b1 to the power of r. Again, that would be like putting a power 5 on the x minus 4. That means we have to break apart this according to this rule. And notice the pattern. If the repeated factor is to power r, we write down one term to power 1, a second term to power 2. We're building up until we get to the rth power, all the way down right here. So if a power 1 comes up here, maybe it's x power 2, or here 2x plus 3 power 5, we would have 5 new terms until we get to that last one. Well, that's what the decomposition theorem is saying. It's easier to just show it in an actual definite example. So here's that example down here. Any questions at the moment before we try it out? Okay, one thing we should also train our eyes to look for is, does the decomposition theorem even apply? For example, the numerator is of degree 3 due to the x cubed term, but what would you all say the denominator is in degree? Exactly, this would be degree 4, because there's an x cubed here when you multiply x plus 7 cubed. Multiply by this, it would climb up to x power 4 if we expanded all of that. So that's to degree 4. Let me just drop down a line a little bit. That means this one's a nice problem. The denominator is fully factored, so we can just launch right into the decomposition. The thing that's new about this decomposition is that right there, that's the repeated factor. The numerator can be pretty complicated, but as long as the degree is below the denominator, we ignore it in the decomposition. We just go a divide by the first factor, x minus 5, plus, let's go just down the line of the alphabet. I'll call this b. Next, we're going to put down x plus 7. Starts off at power 1. That's what this first term is saying. There's no power on it. Then we build up to the next factor, plus c, or you could call it b2 if you prefer. Divide by x plus 7 to the power 2. That's what's going on here in that term. We go all the way up to the rth power, and our problem r is 3. So we just need one more term to finalize this. We'll go plus d divide by x plus 7 to power 3. So again, that 3 there is playing the role of r in this theorem above. Now this would be a pretty complicated problem, but you know what? We could solve this for all coefficients a, b, c, and d. It would just take a lot of work. That could be a 20-minute problem, writing this down really fast, making sure we're not making mistakes. So we're not going to try to do those kinds of questions on the exams. Those are too involved. But there could be a couple problems in the homework that do get a little bit longer. We'll do related problems just like those on the notes. But as far as exams go, we have to control the length of the exam. So I'm not going to throw something that's going to take loads of algebra to try to just get to a point where you can integrate. It'll all be pretty manageable. Well, any questions, folks, with what happened new in case 2? Okay, so we have case 1, where everything is a distinct factor. Sometimes you have to actually literally factor the denominator to reveal it. One of those is repeated. We're in case 2, but it's highly similar. This is the new part. And so here's where it gets really interesting. There's some pretty bizarre algebraic facts about the real number system as it relates to polynomials. It turns out, if you're thinking about polynomials being irreducible, you're talking about having no way to factor it whatsoever. But over the real number system, the only irreducible polynomials that ever come up are quadratics. That's kind of an interesting fact. If you go up to a cubic, you can find a root to that, which means it will factor, and so on. So the quadratics are the weird ones as far as polynomials are concerned. Sometimes they don't factor. You need complex numbers to make it work. The test for that is the discriminant. Your quadratic factor will be ax squared plus bx plus c, depending on those coefficients, a, b, and c. That discriminant right there in gray is going to test whether you can factor this or not using real numbers. So if it's 0, then I thought I said something over here. If this is 0, then this whole part is irreducible, is what I was trying to say here. Let me just highlight that. And I think this deserves an extra note just to be really specific. That shows that ax squared plus bx plus c is irreducible. So if that happens, if one part of q of x has an ax squared plus bx plus c, then this is the new thing that we put in the numerator. We have put a linear function up above. So it'll be ax plus b, two coefficients, whenever this emerges. So that's kind of bizarre in a way. But this is also sort of confusing. The way to get mixed up by this is if you had a problem that goes like this. 5 over x squared, for example. Let's make it plus times x plus 3, just to make it more interesting. If we were going to decompose this one, sure, there's a quadratic, there's x squared, but this portion right here is really case 2, not case 3. So just because something to power 2 comes up doesn't mean we'll have the ax plus b in the numerator. It really has to be an irreducible. X squared is not, because it factors as x times x. So this decomposition here would be indicated by a over x. We're at power 1. Because it goes all the way up to power 2, we need to go plus b over x squared, then plus c over x plus 3. So that's the big danger with case 3. You're looking for specifically things with a negative discriminant. That's not the case with x squared whatsoever. That would have discriminant exactly 1, which is positive. So let's try this out down below. Here on the x minus 5, that was linear, so we're not as worried. But this one's the quadratic. The first thought we might have is, can we factor it? If we can using real numbers, then we're all the way back up to case 1, it reduced by factoring. But if we can't factor it, we'll know right away just by checking out the discriminant. Sorry, let me fix my colors really quick here. So the discriminant is b squared minus 4ac. So that will be equal to coefficient b is over here, 1 squared, minus 4 times the coefficient of a is also a 1, times the coefficient c is a 7. And what did I just do here? Hang on, let me try again. I already have a 7 somehow. A was the 1. I think I drew a 7 instead of a 1. Must have been just looking at that next element. C is a 7. There we go. And so this is just 1 minus 28 for a negative 27, less than 0. And that tells us irreducible. So because it's irreducible, we are now firmly in case 3. And we have to be very careful with being sure to put this when we go to that factor. So here's how the decomposition goes on this. We go just starting over here, just because we're going left or right, making sure not to miss anything. This is just a over x minus 5. But on this one, because it's irreducible, it's not just a b, it'll be a bx plus c. My letters moved over by 1, so not an ax plus b, I already used up a. Then down below, it's going to be the entirety of x squared plus x plus 7. So that's what a case 3 looks like. You'll notice there's a case 4 below, but it's not too different from this one. It just handles the outcome where maybe that's to power 5. Then you have to start writing down 5 whole terms if that was the case. But this one wasn't repeated, so that made it case 3. Well, any questions, folks, on that decomposition there? Okay, we're getting through them. So the last possibility, case four. Case four is a tough case because you are dealing with something that's irreducible, but it's a repeated irreducible factor. This is the one case where actually solving for those coefficients does become a little dicey. You might need new techniques like the technique of equating coefficients. Some people might want to just full on use linear algebra to solve a system of equations. It gets pretty messy. We're going to avoid case four in the homework, but we will see one in section 7.5 just for the people who are really curious. So case four is an interesting case. It won't come up in the homework, which means I'm not going to ask it on the exam. It's just too long of a problem. But again, we will address it in the next section notes when we're doing the review on integration. This will come up. But let's take a look at this one. This is my claim that we're doing a case four problem, and it has to do with this right here, x squared plus 5. I claim that one's irreducible as well. And now there's two tests for this one. You can check that this is irreducible either by using the discriminant. Let's test it out. B squared minus 4ac in this problem would be, well, there is no b coefficient, so that's 0 squared. Minus 4 times the a coefficient is a coefficient to x squared, times the c coefficient is the constant term. So this is just equal to negative 20, less than 0, so irreducible. But if you have just two terms like this, I think that's working a lot harder than you really had to. There's a different way to think about it. Discriminant is always a great way. It always works. But in this case, you can determine irreducible by taking x squared plus 5 and setting it to 0. So irreducible means we can't factor it, but it also means you can't set that equal to 0 and solve either. Factoring and solving this equation are strongly related. What would happen if you try to solve this? You would get x squared equals negative 5. You would take the square root. X is root negative 5, either positive or negative. Nothing too wrong with that, except x is now a complex number, plus or minus I root 5. This tells us right here, it's irreducible because we can't use real numbers to factor it. Well, in either case, we're looking at something that's irreducible. Now, the idea with this theorem here is, because it's to power 2, what we do is we write it once to power 1. We would write it a final time to power 2. But if that was a power 3 right there by the red dot, we would have to write it down 3 times to power 1, to power 2, then to finally power 3. And notice the numerators are just like in case 3. They're always linear now, divided by a quadratic. Does that make sense to folks so far with the case 4? Okay, let's write this out then. In case 4, starting with this one, the irreducible, only because it came first, I would go ax plus b, or a1x plus b1 if you prefer subscripting. We would have to divide it by not x squared plus 5 squared. We build up to that power. So starting at power 1, x squared plus 5, rinse and repeat, we'll go to cx plus d, divide by x squared plus 5 squared. And here's where we stop, just because the power over here was to power 2. If it was to power 20, we would have 20 terms, the power 3, the power 4, the power 5, until we end on power 20. But we never celebrate early. Make sure you've looked at all factors. There's one last factor, 3x minus 8. So we go plus e, divide by 3x minus 8. At that point, we did it, folks. This is the decomposition. The next hard part about these decompositions, and this is a harder one for sure, is to solve for all 5 coefficients in this problem. Again, we'll look at how that goes in section 7.5, but we're leaving it off majorly on 7.4, focusing mostly on cases 1 through 3. But any last questions, folks, on looking at any one of these decompositions? So the partial fraction decomposition theorem, it's a really weird one. Depending on the mathematics you learned in high school, sometimes this is covered. It's just a way to reverse fraction addition, kind of a weird concept. Now, down below, here's what we're really wanting to do with all this. Sure, it's a neat algebraic trick, but if you're integrating, it's not a neat trick anymore. If you're integrating a rational function, it's just survival. It's a necessity out of nowhere. So here's our first problem of the day where we're going to do the full process. We're going to do the decomposition, solve the coefficients, and then integrate to that. As it stands, I would have no idea how to integrate it. So we start with just the fraction. No, really, let's start with the denominator. We always have to have that fully factored, so let's make that our step one. So we begin by factoring the denominator. It's 2x cubed minus 10x squared minus 28x. Like before, we want to pull out the greatest common factor. Anyone spot what it is? Good call. 2x factors out immediately, leaving behind x squared minus 5x minus 14. Then the quadratic right here, it could be irreducible, but sometimes it's faster to determine that just by trying to factor it. Don't like those parentheses. Let me try it again. So we'll split x squared as x by x. We need plus and minus. 14 is more forgiving. 2 and 7 is probably our best choice here. So I'll go a -7, a +2. The check is that this times this is -7x. That's +2x. So we've nailed the middle term, -5x. That's always the thing that we're mostly going for in the factorization. Now that we have the factorization, in step 2, we use the decomposition. Let's just say decompose. So here we want the entire fraction, 2x plus 5. It's now being divided by our factorization. We might as well just throw that in. I want to associate 2x just as a visual reminder for my eye that that's going to be a whole, don't know why I'm pointing with my finger, I'll use this dot. That's going to be a whole denominator for one term. All of it goes together, the 2 as well. Then next is x plus 2, x minus 7. And now that we're looking at this, notice that there's 3 factors. They're all to degree 1, so they're linear. They're all different, so we have 3 distinct linear factors. That means as far as the composition goes, this is case 1. Kind of the friendliest case ever. This is a fast one for solving for the coefficients on. Here's how it goes. For the 2x, we go a over 2x. Then just move over to each factor. B over x plus 2 plus c over the final factor, x minus 7. Now, to solve the coefficients, there's several methods. But in cases 1, 2, and 3, the method that we typically take, which is highly effective, is just clear the denominators. So if you clear the denominators, here's what it would look like. The left-hand side is just a 2x plus 5 equals, over here, it's going to be a times x plus 2, x minus 7, and so on. But let's study this really quickly right here. Does that make sense to folks right by the red dot, how we got those 2 factors here and here? How about for folks in Zoom? Does that make sense right there by the red dot? Okay, doesn't look like it's too bad. If you're still feel like it's kind of foggy how we got that, there's an additional thing that you can do. Clearing the denominators means you're multiplying by 2x, x plus 2, x minus 7 here, and then the full denominator gets vaporized. We just get 2x plus 5. But we also have to multiply it here, so it'd be times 2x, x plus 2, x minus 7, and here the cancellations go this way. 2x's cancel, and we have the other opposite factors. So it's like a strange numerical game where if you see an x plus 2, You delete the x plus 2 and just carry over the other factors. Let's just write this in just for the sake of the explanation. The only downside with this step is that it takes a lot of writing, but it's a precise way to go because if you're looking at something, it's easy to know what carries down by just seeing it on paper. So even though it takes a while to write all that out, it is valuable in a certain sense. So cancellation goes that way. Then plus b. New cancellation over here is x plus 2 going this way. So we would just have 2x, x minus 7 surviving. Then last is x minus 7 canceling here. So we have plus c times 2x, x plus 2. So that's our brand new equation that we must solve. Any questions so far, folks, to this stage? Okay, as we're going through this problem, one thing you're going to notice is that it's a pretty long problem that we have to get through, but it is kind of a nice problem in a certain sense. It's not like section 7.3 trigonometric substitution. That problem is long and it's technical, like every single step is a pretty big step. The steps we're about to take are not as technical, so even though it's long, just be precise with your algebra. It's not as bad as 7.3. I've always wondered why we do 7.3 first. It's a lot harder in my opinion, but maybe it's because there's more to absorb here. Once you get familiar with the decomposition, the algebra is not so bad to get through. So this is now our step 3. Solve coefficients. When we say the coefficients, we're referring to the a, the b, and the c. Because if we can plug those into the numerators here, integrating these three terms rather, is straightforward, whereas integrating the big mess here looks like a total mystery how it should go. Solving for the coefficients is really fast in case 1. Here's what we do. If you want to solve for the coefficient a, you just want to pick one value for x. There's one specific value that will solve for a as a coefficient. Anyone see what it would be? One thought is, if we do want to solve for the coefficient a, this coefficient should be deleted by choosing the right value for x. How about a 0? If you plug a 0 in right here, b vanishes in your equation, c vanishes in your equation, and you can pick any value for x whatsoever. So go for the easy ones, or else we'd be solving a system of 3 linear equations and 3 unknowns. That's more of a linear algebra problem. So instead, we're going to do this. Because we're targeting a, we didn't have to go for a specifically, but if we were, we'd pick x as 0. But from here, pick a -2, that would work. From here, pick a +7, that would work as well. You're solving for the other coefficients. So just pick something that's going to make a factor go to 0, in other words. I like to start off with 0 on this one, so let's do that. X equals 0 implies, the right arrow just says, the last equation is going to imply another equation comes in. We plug 0 everywhere in the equation above. So the left-hand side is 5 equals, over here, this is a times 2 times -7. And the rest of this just vanishes. I'll go +0 just to say specifically, they're gone. Now we have one equation and one unknown. We can make that work. That equation implies 5 equals -14a. And so therefore, a equals -5/14. I'll highlight that in blue just to make it easy to find when we go to use that value. And that's 1 down, 2 to go. So a is determined. Now we need another value to solve for either b or c. We can't reuse a value we picked. You can use x equals 1, but you're still working way harder than you have to. So like we said, try maybe like a -2 or a +7. Let's go -2 and see what happens. If x is set to -2, we'd be plugging -2 here. So that's -4 plus 5 for a 1. -2 here gives us a 0. I'll put in that 0 just as kind of a just way to be organized and say I didn't forget about it. We did compute it. Negative 2 here will allow the b coefficient to survive. So that's the one we're solving for. Will be b times -4 minus 9. Finally, -2 here will give us a 0. So just a +0 on that one. Now that's a nice equation for coefficient b. This now implies that 1 equals 36b. And we've got a coefficient. B is 1/36. Provided the algebra didn't go sideways at any step. Does that look all right to folks so far? Okay, almost there. One last one. So we picked a 0, we picked a -2. Now we could pick a 1 and make it work, but you're working really hard. You ought to pick a 7, something that makes the denominator go to 0 once again. So we'll say set x to 7. That will imply we have 14 plus 5 on the left-hand side, so a 19. 0 here. 0 here as well. You have to love the zeros. And then 7 here is more annoying. So this is going to be c times 14. From here we have times 9. Let's solve this real quick. That means 19 is equal to 9 by 14. That's like 90 plus 36. 126. Okay, 126c. Thanks for the help on that one. Arithmetic is not my strong suit, especially at this hour. So c is now equal to 19 126. So we have a, we have b, we have c. We're just going to plug in those values here, here, and here, integrate the result. Any questions so far, folks? Solving the system? Okay, so now that we've solved the coefficients, step 4 is like the punchline to all of this work we did. We'll just say here, integrate. So we go back to the original integral. It was this thing right here. We're setting it equal to the antiderivative of, you want to look back up here in step 2, the form of your decomposition, because all you're doing is plugging in values where a, b, and c are. So for a, it's -5/14 divided by 2x. Even though we visualize canceling here, that was just to get to this equation to solve coefficients. We still go back to this and use it in this format. Then b coefficient was 1/36, so plus a 36th. It's divided by x plus 2. Then finally plus 19 126. These are some interesting numbers. Divided by x minus 7 dx. And this is kind of the funny thing about calculus. The left-hand side to most people looks more simplified than the right side by far. That's complicated, right? But it's all context sensitive. If you're integrating, this is the complicated thing. The right-hand side is the simplified version for integration in this case. So here's how it goes. Notice all the denominators are x to power 1. That means we're just going to get 3 natural logarithms with absolute values. But regrettably, my first one is kind of the trickiest one. Let's view this at scratch work and see how this could go. If I was going to integrate that, I would revisualize it as -5/28 times 1/x dx. That's a good view to take because we're combining the -5/14, dividing it by 2 to get the -5/28. But also better reveals the 1/x, which is giving us our natural logarithm. So this turns into -5/28. Natural log, absolute value of x, plus a constant. So tricky one right off the bat. Does that make sense on how we got that coefficient, the -5/28? Okay, with that out of the way, here's our full answer to this whole thing. Antiderivative of this rational on the left is just a -5/28 natural log absolute value of x. Then we go down the line. This is a 36th natural log absolute value of x plus 2. Going down the line further, plus 19/126. Natural log absolute value x minus 7. Add the all-important constant of integration, and we've got it, folks. This is the antiderivative of that rational expression, expressed as lots of logarithms. And for folks who are very fluent with properties of logarithms, you might say, let's combine them into one single logarithm, but you never have to do that. If you leave your answer just like this, I'm okay with that. You need a good reason to try simplify a whole bunch to take this further. These are always appropriate stopping points. So we did it, folks. This boils down to really just finding those as antiderivatives. Sometimes these terms are a little bit more complicated, so we have to take extra care. But this is a pretty similar problem to what you could see as a homework question. It would make for an okay exam question, but the rest of my exam would have to be a little bit shorter because it is a long problem. Any last questions at all going through this one? Okay, because these kinds of antiderivatives are coming up a lot, let's write down a couple just for the sake of practice for stuff that we should be on the lookout for. So this is just a collection of just random integration problems for the sake of practice. One integration problem that didn't come up was 1 over 2x minus 5 dx. It's still a natural logarithm. It'd be the natural logarithm, absolute value, 2x minus 5 plus a constant, but this is not the full antiderivative. Anyone spot what should be right in front? Exactly. If you put a 1/2 in there, the 1/2 is because of that coefficient 2, you have the full antiderivative. So notice ours was an x plus 2, x minus 7. Coefficients here were 1s, so that's why we didn't have to put anything in front other than the upper coefficient here. So that's one that definitely didn't come up. The other one we definitely should watch out for is antiderivative 1 over x squared plus 1. It feels like it should be a natural logarithm like before, but this one is different. Anyone see how this one goes? Good call. I mean, it's confusing written this way. Usually it's a 1 plus x squared, but we should spot the difference even if it's changed. Good call in either case. Write either tangent inverse or arctangent. But again, watch out for this. It's a pattern break out of nowhere when we expect lots of logarithms. This can throw us off. Another one that can throw us off is maybe something like, say, maybe it's a 5x divided by, let's go with, what was I going for here? Maybe 2x squared minus 4. This is another one that can come up. It's not a tangent inverse. It's actually more similar to this one right here. This is one where I probably wouldn't try to do it as a one-step problem. I think this is a good one to do as a bona fide U substitution. So let's give it some extra space to make it work out. So when this comes up, I would take the U substitution in my homework just to be extra careful. If you see what it should be and you can do it in your head, sometimes our author actually does that with these. I wouldn't take off credit for it, but just make sure that you're ready to go with that on an exam setting. I think for an exam setting, this is more stable. Just try the U substitution. U ought to be at 2x squared minus 4, the entire denominator. So that's differential. Du is 4x dx. I should have put a 4 there, but let's stick with the 5 that we've got. We'll get a 1/4 du is x dx. So this part, x dx, turns into 1/4 du, and we get a 4th. Antiderivative, oh, and there's a 5 there. Let me put out that 5 as well. A 4th came from the differential over here. The 5 that you see came from the numerator over here. It leaves behind 1 over u du, because we've selected the denominator as our u in the U substitution. So this is the reason the natural logarithm comes up. We have a 1 over u again. It's now 5/4. Natural log absolute value. Add in your constant, and then just unwind your substitution. 5/4 natural log. Here, I still need my absolute value because 2x squared minus 4 can be positive or negative depending on the quantity x. So that stays in. If it was a +4, you could drop those absolute values if you want, but if you left them in, no harm, it's still completely correct. Let's go back to the right thing, the actual negative sign. And these are the things to be aware of. This one is tricky because there's really a chain rule here when you go to verify this by differentiation. This one's tricky because it's a tangent inverse out of nowhere. And this one's tricky because it is a proper U substitution. It's a good one to write out the steps for, just to be careful. Well, again, those are the main things to watch out for. What we'll do next is just another problem along these lines. Any other questions about any one of these kinds of integrals? Okay, well, here's our next problem. We're doing a definite integral next. It seems like definite integrals don't get enough attention, so I try to inject a few in the homework as well in the lecture notes. Our goal here is just to find the antiderivative. Then we have to evaluate it from 0 to 1. So it's like an extra step from the prior problem. But as you're eyeballing the denominator here, which case in the decomposition theorem would you say we're at? Absolutely, folks in class are saying case 2. What makes it case 2 is there's a linear factor here, x minus 2, but it's a repeated linear factor since it's to the power of 2. So that means when we go to start this one off, let's call this a step 1. X squared plus 1 divided by x minus 3, x minus 2 squared becomes, notice we did skip a step because our denominator is fully factored. So we're just launching right into the decomposition. Goes a over x minus 3 plus, now this is the one we have to be a little bit mindful of. It's a repeated factor, so we start at power 1. So that means just put in x minus 2. We add in another term to the second power, so c divided by x minus 2 squared, and then we stop because we've matched up the power at this stage. So there's our decomposition. All we need now to do is clear denominator, solve for coefficients. So that's our next step 2. Let's try it out just visualizing what clearing the denominator looks like. Let me know if it seems vague, and I'll put in the extra information. So if I'm clearing the denominator, I'm visualizing this whole thing multiplying here. So now it's gone from that denominator, just a x squared plus 1. But when we place it here, x minus 3 cancels. The survivor is just x minus 2 squared. So a times x minus 2 squared would go here. Then visualizing it going into that location next. It's plus b. X minus 2 is to power 1. So it just drops this power to x minus 2 power 1. The survivors are x minus 3 times x minus 2 after cancellation. Then one last time, take that whole denominator that's been lassoed, throw it over here. Now the full on x minus 2 to power 2, that's gone. Just x minus 3 remains. So we call it plus c times x minus 3. So that's usually how I try to visualize it. I try to imagine in my mind that this is moving over to those 3 positions. Then we just cancel out the denominators to get that line. Well, either way you visualize it or write it out, does that make sense to this step? Okay, so if we're happy with this, that means we're in business. But notice what we said this was case 2 of the decomposition. Because there's a repeated factor, I really have 2 great choices for x. I have a positive 2 to kill this term, a positive 3, and that's it. So we have to be slightly more creative on solving this one. It gets a little harder each time we increase the complexity to higher and higher cases. But we can still go for the low-hanging fruit. Let's try for a 2, a 3, and then we'll pick for something else. So starting at x equals 3, right arrow to say this implies a new equation occurs. Plugging 3 here gives us 9 plus 1 for a 10 equals 3 here just gives us a positive 1 squared. So this turns into just a times 1. Here we get plus 0 and plus 0 as well from over here. So that means the equation's immediately solved the moment we dropped in x equals 3. We now have a is 10. 1 down, 2 to go, but only one more good x value to choose. We have to get creative on the third one. Well, if we chose x equals 3, x equals 2 is the next natural choice. X equals 2 will then imply putting 2 here, so 2 squared for a 4 plus 1, we're up to 5. 0 on the first term on the right-hand side, plus 0 on the second term, plus we have c times -1 on the third term. And that one's immediately solved. We just divide by -1 or multiply by -1, same difference. We get c equals -5. So we solved for the c coefficient. Last is our b coefficient. Any questions so far to this stage? Okay, so finally, this is where it's a choose your own adventure kind of problem. We need a good creative choice for x here. Some people could put 17, and it absolutely works, but you never want to work too hard. Any volunteers for a good value? That's a good question. You could actually plug these in. Yeah, absolutely. But we could even go for a slightly simpler one, I would say. A 4 would work. Sorry, say again. One higher up from, oh, you mean the 3 right here? That would work as well. But I would say you can even make it easier on yourself. Any volunteers for an even easier value than 4? How about just an ordinary 1? Plugging in a 1 there is going to make everything as easy as possible. Well, 4 has got something going for it now that I'm looking at it. Plugging in a 4 would give us a 1 here and a here, so it does simplify it to a good degree. Usually 1's a good choice, but you know what? Let's try out a 4 just to see how it goes. In this particular problem, I think 4 is a good option because of the x minus 3's that occur. So if you let x be 4, the good news is any number here would work as long as you're not reusing 3 and a 2. You're not getting new information there. Or here is going to give us 16 plus 1 for 17. Or here is going to give us, well, notice we know what a is. We have the value for a, we have the value for c, so what we should carry down is 10 in this position. It's multiplying 4 minus 2 squared. That's just a 2 squared for a 4. We don't know that coefficient. That's our whole objective, to solve it. So plugging in 4 is going to give us a 1 and a 2. Then finally, on the c coefficient here, we'll go -5. We're plugging 4 right into this location, so that's just going to be a times 1. And yeah, this is a great equation to solve. We're not working too hard, so 4 is a great choice on this one. Let's see what this comes out as. This last coefficient looks like a doozy. It's 17 equals 40 plus 2b minus 5. Let me double check that. Yeah. So we have all that. We have 17 equals 35 plus 2b. Subtract 35 from 17. Let's treat ourselves to a nice calculator. 17 minus 35 gives us a -18 equals 2b. Finally, division tells us b equals -9. And we've got it, folks. This is going to be the last coefficient that we'll plug in. Again, because we're in case 2, the problems are getting a little bit longer. This probably wouldn't make a great exam 1 question. It could make a better final exam question because we just have the extra time to take on these problems. But one thing you might want to consider when you're learning this stuff for the first time, say you're doing it as a homework question, you ought to write this out because we're expected to do it on an exam. So this is just going to be for the sake of safety, preparing for exams. But you do have a check. The check is through technology. Open up a browser. Go to wolframalpha.com. And wolframalpha.com is really good at doing a decomposition. Again, use this only for a check in your work because we do have to show this stuff in our homework because we have to do it in an exam setting. But if you did all this in your homework and you're about to integrate, you want to know right away, are you integrating the right thing? Did I make some weird sign error here? There's a lot of operations we took. So our check would look like this. Say apart, kind of a funny function, x squared plus 1, x minus 3, x minus 2 squared. Just type it in this linear kind of way. Let's see what it does with that. They want to sell you a product, so I would ignore that part right there. Just scroll down. And they say the decomposition should look like this. Let's see how we did. They have a -9 above x minus 2. That's our B coefficient. Hey, we have a -9, so we're on the right track there. They have a -5 above x minus 2 squared, so that's the C coefficient. We have a -5. Finally, a +10 above x minus 3, and we have that +10 lined up. So again, this is something that you could try out. Write in the apart function like that, and it's a great help when you're learning this stuff for the first time in homework. I'll put out a screenshot just to show how you can do all that kind of stuff if you want to duplicate it as a check. Okay, well, aside from that down there, we still have to finalize our problem, so let's put in the coefficients and integrate. Any questions at all so far, folks? Either with the check we showed or what we did by hand? Okay, so here is our step 3. We're finalizing everything and we're integrating this up here. So antiderivative of x squared minus 1, x minus 3, x minus 2 squared, dx becomes the antiderivative of, back up here, take the a coefficient, 10 divided by x minus 3, and the b coefficient is a -9 divided by x minus 2, and our c coefficient is a -5, which is divided by x minus 2 squared. And let's pause maybe just for a bit on this portion. When we were looking at the integrals right above, that one didn't come up. I forgot about that one. That one is unique all into itself, so we have to watch out for when this one comes up. So this one is neither a tangent inverse. It's not going to be a logarithm or anything like that. We'll show how to integrate that when that comes up. But one thing I did forget here is, oh, this was a definite integral from 0 to 1. So let's copy those in as well. Can't sneak out of that so easily. We're probably going to have to go down a page. I usually use these arrows just to alert us we need a new page to finalize this one. And so let's go turn by turn, starting off on this one. The power of x in the denominator is 1. The coefficient is 1. So all we do is we take the coefficient 10, natural log absolute value of the denominator, x minus 3. So that's a great antiderivative. Same on this one, go -9, natural log absolute value, x minus 2, and we're all set. And now this one, well, you can pull out the coefficient -5, but now we still need to integrate x minus 2 squared. Let's show how to do that over here on the margin. Antiderivative of 1 over x minus 2 squared. Think of this as you're not doing anything too different as integrating 1 over x squared. It's really the same sort of problem. It just looks more complicated because it's x minus 2. If you're integrating 1 over x squared, good advice is take your base, promote it up to the numerator. X minus 2 to the power -2. In this configuration, you're just undoing the product rule, using it in reverse. It means the power goes up to a power of -1. So we go up in antiderivatives. Once we obtain the power, we divide by it. Oh, good question on that one. Looks like a miscopy there. Thanks for spotting that. Should have been a 2 right here. So put in the actual 2, not the 1 there. New power of -1, we just divide by it. and add a constant. Looks kind of funny in this configuration, so you could rewrite it as -1 over x minus 2 to the power positive 1, so just x minus 2, didn't really need in parentheses either, and that's our antiderivative. So we went from power 2, the antiderivative brings it to a power 1, but there's an extra negative sign there, and the only way I'm really able to spot that negative sign is, that's my strategy, bring the base up to the numerator and go from there. So all of this gets conveyed over here as -5 times -1 divided by x minus 2. But then the problem doesn't want to quit. We take this whole entire thing, we're evaluating it from 0 to 1, because this was a definite integral this time. This is the major part of the problem, though. We obtained the antiderivative. Now it's just a little bit of arithmetic to get through it. Any questions at this stage? Okay, doing the normal things, we begin with the upper limit of integration. Everywhere x is to the left, replaced by 1. So we get 10 natural log of 1 minus 3. So that's absolute value of -2. Just becomes a -2, or excuse me, a positive 2 like this if you drop the absolute value. Then it's -9. Natural log, absolute value of 1 minus 2 just becomes natural log 1 altogether, since that's a -1 there in absolute value. This is a +5 altogether from the double negatives, divide by 1. Oh, hang on, divide by -1. There's an extra negative sign that emerges there, 1 minus 2. Then go minus a bracket, and we do it all over again with coefficient 0, or input 0 for x. So this would be 10 natural log absolute value -3, so just a 3, minus 9, natural log absolute value of -2, so that's a 2. And now plugging 0 right here by the red dot means we have -5 times -1 divided by -2. So that's a 5/2, positive. It's a bit of a mess, but we've got it, folks. This is the exact area under this curve from 0 to 1. Well, signed area. There's like terms here, there's cancellations, there's things to clean up. So let's do the final steps of just presenting our answer a little bit better. For example, this is gone because natural log 1 is 0, so we can just clean that off. We have a 10 natural log 2. Here, because I have a 5/2, let's multiply this one by 2 over 2, call it -10/2. Distributing here gives us minus 10 natural log 3 plus 9 natural log 2 minus 5/2. And we have like terms now. They are natural log 2s. We have 19 of them altogether. 19 natural logarithms of 2. I think I have a sign error here for some reason. -15. We had a -10/2 here. Let me take a look at that. I don't know why, but this looks a little odd to me. Anyone see anything funny with those signs? Plugged a 0 on this one, so that should have been a -5 times -1 divided by -2. Well, that should have been a negative, shouldn't it? When we plug in 0. Does that look better to folks with a negative there? So in other words, if I have a 0 in this location, there's 3 negative signs all being multiplied, divided. I should have put a negative sign right there. That looked really funny. And that means that negative sign conveys down here to a positive. Suddenly that looks a little bit better. -10/2 plus a 5/2 gives us a -5/2 minus 10 natural log 3. I would have never spotted that error. It was my mistake, but I practiced this problem this morning, so it just looked odd to me. I was expecting that number. Well, we did it, folks. This one was a little bit tougher because it was a definite integral. And watch out for this kind of antiderivative when it comes up. It could be 1 over x minus 2 to the power 3. Same kind of strategy. But looks like we did it, folks. We only have about 2 minutes and change to go. We obviously cannot solve this problem in 2 minutes. So we'll come back to that when we are on Thursday's class. Any last questions or comments before we call it a night? Okay, well, have a great night, folks. We'll be back on Thursday, finishing off this notes, and then we'll walk into section 7.5. That's really just a big review section of doing anti-derivatives, section 7.1 through this section 7.4. But have a great night. See you all on Thursday. Yep, you betcha.
I have one question.
Go ahead.
So why is it x minus 2 and then x minus 2 squared?
Sorry, you were breaking up a little bit there. What was that again?
So why is it x minus 2 times x minus 2 squared?
X minus 2 times x minus 2 squared. Are we looking, oh, right over here?
I
So are you
think it
saying
shows it on step 3, but it also showed it on step 1.
on step 1? Gotcha. Let me look up here. Oh, I got you. You're referring to this x minus 2 squared. So the x minus 2 squared came because of the power 2 on this one. Whenever there's a repeated factor, that's what made it a case 2 problem. We start at x minus 2 to the power 1, but then if this is to power 2, we have to go to x minus 2 to the power 2. And just to add a little bit more to that question, suppose that was to power 4, the problem would be a lot worse, but we would have to go plus d x minus 2 to the third power, and then we'd have to go plus e x minus 2 to the fourth power. So whatever the power is right here, we have to list out all of those terms until we get to that high power. Does that make sense with that question there?
Yeah. Um, there was another question I had just a little higher. It was with regards to like 1 minus x squared, I think, or x squared minus 1.
Sorry, it's really hard to hear you, Jose. You're breaking up quite a bit. It might be your internet connection, but could you try again?
A little higher up in orange, there was a side note where it was x squared minus 1. Wouldn't that go to x squared plus 1 and I mean, x plus 1 and x minus 1?
Gotcha. Let me see here. You said it was an x squared plus 1?
I remember it being in orange as x squared, either plus
Gotcha.
1 or minus 1.
Let me see if I can find that here. I had the x squared plus 5 here, but as far as an x squared plus 1 in orange, huh. Well, what I could do is,
I think you just passed it.
oh, did I? Gotcha. Oh, this right here again?
No,
Is
I
this the,
think it's gone.
oh dear. Well, we could write it down again. Let me get another pen tool to add it here. Do you remember how it went? It was something like 1 over, you said x squared plus 1?
Yeah, because it was like one of the things that we need to watch out for because it was tricky.
Yeah, this one is extremely tricky in my opinion. So if you see anything like this, one thing you can do is go to section 7.5. Section 7.5 has a pretty great table for the purposes of our class. And the ones you're looking out for would be, thank you, this right here. It's this formula. Let's bring it into the notes. Where instead of an a squared, we have just a 1 being placed right here. So this a squared re-expressed as a 1. The answer is always a tangent inverse. So it would go tangent inverse. First, it's a 1 over a, but if our a is a 1 right here, it's just a 1 over 1 that goes into that location. Then an x divided by a would just be x divided by 1. plus a constant. So yeah, this is a big one to watch out for when this one comes up.
Okay, thank you.
Yep, absolutely. Sorry for the trouble with the technology. So sometimes you break out, you're breaking up a little bit, but you're coming through just perfect right now. I don't know what changed, but that's good to know that your microphone is working just fine. Questions over here?
Oh, kind of. So on 7.5,
Yeah,
I think you did it wrong. I'm not, questioning your expertise,
that's a very strong possibility. Absolutely.
but I got -32/9, and on the
Yeah.
homework you have -28/9.
Negative 32/9. And which palm was this one?
11.
Palm 11 goes definite integral 0 to 4, root x natural log root x, or the root of
Y.
x.
It's
Oh, root y natural log y.
Yeah.
So to integrate this right here, you've
that's
got,
integration by parts. So
yeah. Oh, but you had that other method that you were going for. Let's just check out our anti-derivatives. That might be a little bit quicker to compare. So my antiderivative on question 11, this is 7.5. Gotcha. Oh, this is where it's those random integral problems.
Yeah.
Kind of out of order.
Trying to figure out what to do.
So let's see, on 11, I did integration by parts like you mentioned, and I got, this is my antiderivative. 2/3 y to the 3/2 log y. Log y. And so on yours, let's see,
Well,
there's 2/3, the natural log y to the 3/2. Yeah, it looks like you've got that antiderivative right there.
the reason I asked is because I plugged it in because
Mhm.
I thought I did it wrong. And so I made my calculator do it. So it was the square root of x times the natural log of x dx. So we get that.
Yeah,
And when you do, God, what did I put? 16 natural log of 4/3 minus 32/9. Oh, I guess I did it wrong. Yeah.
3.8.
Yeah.
You know, there's another pretty robust check on this. You could also go up here,
Yeah.
integrate. We're integrating square root y, natural log y, from 2 to 4. Oh, 2 to 4. So this said,
Oh, no, I was right. You had a 4.
oh, 0 to 4, gotcha. Let me put in, oh, it looks like it's a 1 to 4.
1
You
to
know,
4, yeah.
maybe that could potentially be
That
the
might be
issue.
why it
Yeah,
messed me up.
just a slightly different integral we're doing. So it says this should come out as, let's see, what they give us. For the antiderivative, we've got 2/3 y to 3/2, 3 log y, minus 2 plus a constant. Assuming a complex value logarithm, interesting. And they're saying that this should be approximately equal to about a 4.2825 on theirs.
Yep.
Is that what you're evaluating too?
Mhm.
Gotcha.
So I think I did do it wrong then. If I plug it in, because then it's the natural log of 4. The natural log of 1 is just 0, so it doesn't matter what's on the other side.
Yeah, I think that's the whole reason it's integrating from 1 on this.
Mhm.
And yeah, now that I think about that, we wouldn't be able to integrate from 0 because natural logarithm of 0 would be undefined at that value.
Mhm.
Well, we might be able to. In section 7.9, we have a method for that.
Let's see. You might be totally right. I'm probably messed up somewhere.
I sadly don't write a lot of details on my solution, so it's pretty terse, pretty brief how I got there.
No, your solution's right.
That works out then?
Yeah, I
Cool.
think I had messed, like, I think I did this right, but I had messed up, because I think if you see here, I put a
This is
0.
because of the 0,
Yeah.
yeah, gotcha, cool.
And then, here. So it was a trig integral, and then
Yeah,
We had a 1/2 because I did the reduction formula to 1 + 2 cosine, and then I integrated the cosine to sine and did the reduction. But because we have this 1/2 out here, wouldn't this 2 that you get from the reduction cancel out?
let me take a look. So yeah, you had the 1/2 from the reduction, and you're still integrating this part right here, right? The sine two theta.
Well, it's already integrated because it's 1 + cosine 2 theta, and I split up the integral.
Oh, gotcha.
Yeah.
But the antiderivative of the cosine two theta here would give you an extra 1/2 on that.
Oh, yeah, you're so right.
Because of just
Oh,
that two theta. throwing
okay,
it off.
that makes more sense.
Cool.
Thank you.
Yep, absolutely.
Yeah, those tiny little mistakes are killing me.
You know, it's, the tiny little mistakes do kill you, but when these are graded, it's by partial credit. I'm mostly looking for,
That you.
do you understand the process, not did you mess up a negative sign? That's not really the calculus.
Okay, well, thank you so much.
Yep, absolutely.
Well, I'll make sure to get those.
Sounds good.
Which, variable come?
I do not. That's the only one that they've never given to me yet.
Really?
I think it'd be a fun one to teach Calc 3, but that's the one where it actually requires a good amount of preparation to
Oh.
really get your notes and coursework going on that.
Well, 'cause on that one, you can integrate with respect to each variable, right?
Yeah, you can do
Or like
multiple
Excel.
integrals and all sorts of stuff like that. Yeah.
Oh, so I was curious, I know you said like graphing calculators aren't allowed. I
Mhm.
don't have any other than the TI-84. I don't know if I could get
I do have a class set that I can bring, so
Yeah.
I'll have some extras.
cause I was like, I know it's class rules and
Mhm.
you make an exception, you have to make. one
Yeah,
for it.
yeah, it gets a little weird. It's mostly because of the testing center in Pocatello, actually.
Oh,
It's a
really?
fairness issue where they need to know what calculators are allowed or disallowed, but now I have to be specific to our section as well because of it.
Okay,
So-
yeah, cause like, I bought the TI-84 last semester, cause mine broke. And I was like, oh, well, that's fine, I'm sure the professors will allow it, and then I read the syllabus and I was like, no graphing calculators allowed.
Yeah.
I was just like, oh, well, I guess.
Thanks, you too. Drive safe.